Hi, I'm Ethan Armis, and this is the Physics 2 Lab 3 Circuits Lab. This lab was constructed for the purpose of observing electrical principles as it relates to circuits, including observing the loop rule for voltage, node rule as it relates to current, Ohm's law, which is V equals IR, and the behavior of a capacitor. As a preview for some of the final results, we observed that the current across the initial circuit to be about 0.0205 amps. The 100 ohm resistor had a potential difference across it of about 2.05 volts, and the 47 ohm resistor had a potential difference across it of about 0.95 volts. So part one relates to Ohm's law and the node rule and loop rule and observing voltage and current and things like that. The assumptions that we made going into this is that the batteries are fully charged. Here's a picture of the circuit that you can see where we have the multimeter connected in series. In this experiment, of course, we're observing the circuit as systems and the surroundings to be everything else. We measured the current of the circuit in series due to the node rule, because if we measured in parallel, the current we would be reading would be less than the current of the original circuit. We measured that the current was about 20.5 milliamps or 0.0205 amps, and reversing the connection point of the multimeter would simply make the reading negative. Switching the ammeter to a voltmeter in this configuration resulted in reading 0 volts, because reading voltage in series is kind of like reading voltage at a single point, meaning there can be no potential difference across a single point. So we continue to measure voltage drop across the circuit in parallel in order to observe the loop rule. We measured that the voltage across a 100 ohm resistor was about 2.05 volts, and across the 47 ohm resistor to be 0.94 volts. The batteries are two 1.5 volt batteries, meaning a total of 3 volts is being powered at the beginning. This leaves a drop of 0.01 volts left in the circuit, which we attribute to the resistance in the wires. This shows the loop rule as the sum of two 1.5 volt batteries is 3, and then 2.05 plus 0.94 plus 0.01 also sums to 3, meaning that the total change in electric potential across the circuit sums to be 0. Here you can see the graph that we drew to visually represent the voltage drop across the circuit as you pass through different points on the circuit. And as you can see, the multimeter at the end has no effect on the voltage reading of the circuit. So finally is the second part where we are observing the effects of a capacitor. In this, we assume also that the battery is fully charged, but also that there is 0 resistance in the wire. So of course, the system is the circuit itself and the surroundings are everything else. We created an RC circuit with the capacitor and also 2 resistors, which were light bulbs of 10 and 20 ohms each. We connected the circuit up to 2 1.5 volt batteries, which lit up the light bulbs briefly until they went out. The light bulbs went out because the capacitor was completely charged. No more electrons could flow, eliminating the current of the circuit. This happened once the potential difference across the capacitor was equal to that of the batteries, which is 3 volts. We disconnected the battery and reconnected the circuit as seen by the red line in the diagram. This allowed the capacitor to discharge and act as a power source, which briefly illuminated the bulbs, but then of course they went out once the capacitor was fully discharged. Something to note is while the capacitor discharges, the current is flowing in the opposite direction. Wrapping up, we'll consider this hypothetical. What if you charge a capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? And explain. The capacitor would charge nearly instantaneously as there's no resistance in the circuit. But in real life, this can't happen because even with our best circuits, there's still a small amount of resistance within the wires themselves. So, in conclusion, this lab demonstrated how we can observe electrical principles with simple circuits. It's important to measure voltage in parallel and current in series. Also, capacitors are fully charged once the electric potential difference across them is equal to that of the power source. Thank you.